This is part 9 of the series Applications of Differentiation. In this section we're going to explore concavity, and we're going to determine the open intervals on which the graph of f is concave up or down. Now, in our previous discussion on concavity, we saw that the definition of concave states that if f prime is increasing, the function is concave up, and if f prime is decreasing, the function is concave down. So that implies a second derivative. So let's go ahead and take the second derivative of this function. And before I do that, I'm going to rewrite a little bit. You may be tempted to just go ahead and do the quotient rule, but I'm lazy, so I'm not going to do that right now. So this is 6 times x squared plus 3 to the negative 1. So now f prime is going to be negative 6 times x squared plus 3 to the negative 2 times the derivative of the inside, 2x, which gives us negative 12x over x squared plus 3 squared. So that's our first derivative. Now we don't really have a whole lot of choice. We're going to have to use the quotient rule to find the second derivative. So here we go. F double prime of x equals, I'm going to yank out the negative 12 because I don't want to have to deal with that the whole time, and low x squared plus 3 squared d high, which is just 1 because I pulled out the negative 12, minus high d low. And the derivative of the low piece is 2x squared plus 3 times the derivative of the inside, which is 2x, all over the low squared. So that's x squared plus 3 to the 4th. Now we've got some simplification to do here. Let's give ourselves a little room here. And in each one of these terms, we have an x squared plus 3. So let's go ahead and get rid of one of those in each term. So we have 3 here. This one's going to go away altogether, and this 2 goes to a 1. So let's go ahead and rewrite what we have. So we have negative 12 times, this is x squared plus 3 minus this thing, which is going to be x times 2 times 2x. So that's 4x squared. 4x squared all over x squared plus 3 to the 3rd. And we can simplify a little further. Let's expand this out. So we have x squared minus 4x squared is negative 3x squared plus 3 all over x squared plus 3 to the 3rd. And that whole thing is multiplied by negative 12. And we can make our lives a little bit easier by going ahead and factoring out a negative 3 out of this numerator. So negative 12 times negative 3 is 36. So 36 times what's left on the inside is x squared minus 1, and that's over x squared plus 3 to the third. And there is our second derivative. This is f double prime of x. Now, it made sense because we were looking for an expression where the second derivative is positive and negative. It's going to change from positive and negative where the second derivative is 0, obviously. So that was our test for concavity. So let's take a look and see where this function is 0. So if we set this whole thing to 0, you can see the denominator is going to go away because we're going to multiply both sides by the denominator, and we're left with 0 equals 36 times x squared minus 1. Divide the 36, 0 equals x squared minus 1. X is plus or minus 1. So the second derivative is going to be 0 at negative 1 and 1. So let's go ahead and do some similar tests here. Let's put anchor values at negative 1 and 1. And let's test at negative 2, 0, and 2. And let's see where the function is positive and negative inside here. So we have f double prime at negative 2 is positive. So I'm going to make a U up here indicating concave up. And f double prime at 0 is negative. So I'm going to make an upside down U showing concave down. And f double prime at 2 is positive. So make another U indicating concave up. So to write our intervals of concavity, we can say that we're concave up on the interval negative infinity to negative 1, and 1 to infinity, and we're concave down on the interval negative 1 to 1. Okay, let's move on to another example. So again, in this example, determining concavity of this function, first thing we have to do is take the first derivative. So there's no simplification that we can do at this point. We're just going to have to go ahead and dig in. So f prime of x is low, which is x squared minus 4. D high, derivative of the high, is 2x, and minus high, which is x squared plus 1, d low, which is 2x again. And that's all over low squared. Now to simplify this, we have 2x x squared minus 4 minus 2x times x squared plus 1 all over x squared minus 4 squared. So let's go ahead and distribute these values in the numerator and see if there's some cancellations we can get. So this is 2x to the third. So this times this is 2x to the third, and this is minus 8x, and this one is minus 2x to the third minus 2x, and that is all over x squared minus 4 squared. And we do have a cancellation here, and negative 8 minus 2 gives us negative 10x over x squared minus 4 squared. And that is f prime of x. Bad form here. Okay. Now let's give ourselves some room, and we're going to have to take the derivative of this. So I'm going to pull out that 10. So f double prime is negative 10 times low, which is x squared minus 4 squared. D high is just 1 minus high, which is x, times d low. This is going to be 2 times x squared minus 4 times the derivative of the inside, 2x over low squared. Okay. All right, now again we have an x squared minus 4 in every one of these terms. So let's go ahead and simplify that out. So this goes away, this goes to 3, and that one goes away. So we have negative 10 times x squared minus 4 minus, this is x times 2 times 2x, so that's minus 4x squared, all over x squared minus 4 to the third. This simplifies to negative 4x squared plus x squared is negative 3x squared. So this is negative 10 times negative 3x squared minus 4 over x squared minus 4 to the third. And just for kicks, we can factor out a negative 1 out of this numerator just to make it look a little better. So factoring out a negative 1 times negative 10 is just going to be 10. So that's 10 times 3x squared plus 4 over x squared minus 4 to the third. Okay, and that is our second derivative. Ordinarily, what we need to do is determine where this function equals 0, but if you look inside this numerator, you'll see that there are no points where this real points where this function is 0. These are imaginary. But if you look at the denominator, we do have two asymptotes, one at 2 and one at negative 2. And because the function would be increasing or decreasing without bound at those points, those are our values to test. So here's our evaluation. F double prime is positive here and negative here. And here are our intervals of concavity. We're concave up here and concave down here. Now on to the next section.